Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. An app gets 100,000 photo uploads in 4 minutes. It is 2 a.m., and nobody is awake to add servers or patch an operating system. But the code still runs, once for each upload, for a few hundred milliseconds at a time. With Lambda functions, you pay for requests and the compute duration your code uses while AWS manages the servers underneath. The surrounding services still have their own costs, and Lambda still has quotas, but for short, event-driven work, the model can be incredibly efficient. In the last part of this Cloud Practitioner series, we broke down EC2 pricing so you stop paying for idle instances. Now we are taking the next step. What if you did not have to run an instance at all? AWS Lambda lets you focus on the code and the event that triggers it instead of managing the server that runs it. By the end of this video, you won't just know what serverless means. You'll be able to look at a workload and say whether Lambda or EC2 is the right call. You'll also know how to avoid 2 mistakes that quietly rack up bills or expose credentials: triggering a Lambda function from its own output bucket and leaving sensitive configuration inside your function code. We'll walk through a real Python handler so you can see exactly where those mistakes live and how to fix them. Before Lambda, building an application often started with a server. You chose an instance size, configured and patched an operating system, set up monitoring, and planned for traffic spikes. Lambda changes that model for short, event-driven tasks. You provide code, connect an event source, and AWS manages the underlying execution environments that run the function. When demand rises, Lambda can create more environments, subject to your quotas and the capacity of the surrounding architecture. That does not remove all responsibility. You still own the code, dependencies, configuration, permissions, and data. Serverless removes much of the server management work. It does not remove responsibility for the application. So what exactly is AWS Lambda? AWS Lambda is an AWS serverless compute service. Its classic, and still most important model is Function as a Service, or FaaS. Instead of provisioning a server and keeping an application process running, you write a focused piece of code called a function. Then you connect that function to an event. When the event happens, Lambda runs your code. A file arrives in S3, run the function. An HTTP request reaches your API? Run the function. A message appears in a queue. Run the function. A scheduled event fires. Run the function. For standard Lambda functions, billing is based primarily on the number of requests and the compute duration your code uses. The memory configuration also affects the compute resources available to the function and the compute cost. When there is no work, there isn't an EC2 instance sitting there for you to patch, administer, or keep running just so the function is available. Optional Lambda capabilities and the surrounding AWS services can have their own charges, so serverless does not automatically mean free. Lambda can scale rapidly for event-driven workloads and integrates with a large number of AWS services. That's why you'll see it used for file processing, APIs, notifications, automation, data processing, security workflows, and many other event-driven tasks. For this beginner lesson, keep the mental model simple. Event happens. Lambda runs focused code. AWS manages the underlying compute. Event-driven is the piece people often gloss over. An event is a change. A file lands in an S3 bucket. An HTTP request reaches API gateway. A message appears in a queue, or a row changes in DynamoDB. That event invokes your Lambda function. The function runs a handler, the specific code entry point you wrote, and returns a result or sends work to another service. Sometimes one event triggers one invocation. Other event sources, especially queues and streams, can send a batch of records to one invocation. So do not assume every Lambda call handles exactly one item. The event source determines the shape of the event your handler receives. The mental model is simple. Something changes, an event is created, and your code reacts. Quick checkpoint. A new photo lands in an S3 bucket. Which part creates the event, and which part runs your code? S3 is the event source. Lambda is the compute service that runs the handler you connected to that event. Remember the pattern. An AWS service detects a change, then Lambda reacts to it. When you open a Lambda function in the console, focus on the settings that define how it runs and what it can access. The handler is the code entry point. The runtime is the language environment, such as Python or Node.js. The trigger is the event or integration that invokes the function. The IAM execution role controls what AWS actions the function can perform after it starts running. Environment variables hold non-sensitive configuration, such as a bucket name, API endpoint, or log level. Memory affects the resources and compute cost. Timeout limits how long one invocation can run. Concurrency controls how many invocations can run at the same time. Do not memorize the console layout. Remember the concepts: handler, runtime, trigger, execution role, configuration, memory, timeout, and concurrency. Here is a Lambda function small enough to fit on a sticky note. The handler is the function AWS calls when an event arrives. In Python, the handler typically receives two arguments. Event carries information from the service that triggered the function. Context carries runtime metadata. The exact event structure depends on the trigger, and the exact handler format depends on the runtime, so always check the current documentation for the integration you are using. Logging is useful for debugging. In development, a carefully redacted view of the event can help you confirm what Lambda received. In production, do not blindly print entire events. Requests can contain personal data, tokens, or other information that should not end up in logs. For an API endpoint, you commonly return a status code and a JSON body. The exact response shape depends on the API gateway integration. The mental model stays the same. Event comes in, handler runs, result goes out. Search for Lambda in the AWS Management Console, choose Create Function, and select Author from scratch. Name the function Thumbnail Generator and choose a currently supported Python runtime. For this lab, create a new execution role with the basic Lambda logging permissions. The execution role controls what the function can do after it starts. For example, whether it can read from S3, write to DynamoDB, or retrieve a secret. Do not confuse that with invocation permission. Invocation permission answers who is allowed to call this function. The execution role answers what is the function allowed to do after it starts. Choose Create Function. There is no server size, operating system installation, SSH key pair, or patching schedule to manage. Add VPC networking only if the function actually needs access to private resources. Quick checkpoint. Which settings most directly shape a Lambda function's behavior? Memory controls the resources available to the function and also affects CPU allocation. Timeout limits how long one invocation can run. And concurrency controls how many invocations can run at once. Those three settings are not just technical details. They affect performance, cost, and how much traffic your function can handle. Quick recall check. What does the IAM execution role do? It gives your Lambda function permission to call other AWS services. If the function needs to read from S3, write to DynamoDB, retrieve a secret, or publish a message, the execution role must allow those specific actions. Without the right role permissions, the function can run, but its calls to those services will fail. The goal is least privilege. Allow only the actions and resources the function genuinely needs. Quick checkpoint. How does Lambda function billing differ from EC2 on-demand pricing? With EC2, you generally pay while the instance is running. With the standard Lambda function, billing is based primarily on requests and the compute duration the function uses. The memory setting affects the resources and compute cost. Serverless is not automatically free. Connected services, data transfer, provisioned concurrency, storage, and inefficient code can add cost. But you are not paying for an idle virtual machine just because a function runs for a few milliseconds. Lambda isn't a standalone island. Its real power comes from reacting to events generated by other services and applications. Here are some of the integrations you should recognize. Amazon S3 can invoke Lambda when files are created or changed. Amazon API Gateway can invoke Lambda in response to HTTP requests. DynamoDB streams can provide records representing changes to DynamoDB items. Amazon SQS can provide queued messages for Lambda to process. Amazon Kinesis can provide batches of streaming records. And Amazon Event Bridge can route events or trigger scheduled automation. For Cloud Practitioner, focus on recognizing these common integration patterns rather than trying to memorize every Lambda integration. Ask, what happened? Then, which service detected or carried that event? Then, what code should react to it? For example, file uploaded? Think S3, Lambda. HTTP API request? Think API Gateway, Lambda. Queued background work? Think SQS, Lambda. Continuous stream? Think Kinesis, Lambda. Scheduled automation? Think Event Bridge, Lambda. You don't need to memorize hundreds of integrations. Learn to recognize the architecture. Event source, Lambda, action. Here is the pipeline you will see in nearly every serverless demo. A user uploads an image to an S3 source bucket or to an incoming prefix. That upload event invokes Lambda. The function creates a thumbnail and writes it to a separate destination bucket or a non-triggering processed prefix. Keeping the source and destination separate prevents the function from triggering itself in a loop. And notice the mental shift. You did not launch a server to handle the upload. The event itself invoked the code. If you need to choose between Lambda and EC2, start with the workload. EC2 gives you a server and more direct control over the operating system and instance configuration. It is a strong fit for persistent processes, custom host requirements, long-running sessions, or software that expects to own a server. Lambda functions are event-driven compute. A single invocation can run for up to 15 minutes, so they are well-suited to short, bursty tasks such as file processing, APIs, automation, and event handling. For sustained or predictable volume, compare the total cost and operational trade-offs of Lambda, Lambda managed instances, EC2, and container platforms such as ECS or Fargate. The right choice depends on duration, concurrency, latency, dependencies, and the amount of infrastructure control you need. A standard Lambda function is not the right target when one unit of work needs more than 15 minutes, when the application needs a persistent process, or when it requires specialized host control. For those workloads, compare EC2 or a container platform. For steady, high-volume function workloads, also compare Lambda managed instances with standard Lambda functions and other compute options. The rule is not steady means EC2 or spiky means Lambda. Match the compute model to the actual duration, traffic pattern, latency, cost, and operational needs of the application. Lambda does not boot a whole server for every request. But when it needs a new execution environment, it has to initialize the runtime and your setup code before the handler runs. That delay is called a cold start. Later requests may reuse an existing environment and skip that initialization work, but reuse is never guaranteed. Cold starts can also happen during rapid growth, when Lambda needs more environments than are already warm. If startup latency is critical, evaluate options such as provision concurrency or, for supported use cases, Lambda Snap Start. For this lesson, remember the core point. Initialization can add latency when Lambda creates a fresh environment. Which workload is the clearer fit for a standard Lambda function? A. Photo uploads arrive unpredictably, and each one needs a few seconds of processing. B. An application runs one persistent process, 24 hours a day. The clearer Lambda candidate is A. Each upload is an event, the work is short, and Lambda can scale as uploads arrive. That does not mean every steady workload belongs on EC2. It means the choice should follow the workload's duration, traffic pattern, latency needs, and total cost, not a single keyword. Here is a mistake that quietly breaks Lambda applications, assuming the next invocation will remember what the last one did. Lambda may reuse an execution environment. When that happens, data in memory or files in the temporary directory can still be present. But reuse is not guaranteed. Lambda can create a fresh environment at any time, and different invocations can run in different environments at the same time. So do not depend on local memory or temporary files for shared, durable application state. Store sessions, job status, files, and important records in an external service such as DynamoDB, S3, Elasticache, or a database. Use local state only as an optimization. Use external storage for anything the application must remember. The fastest way to create a security incident is to paste an API key directly into your function code. Do not do that. Use environment variables for non-sensitive configuration, such as a bucket name, a feature flag, or a log level. For passwords, API keys, authorization tokens, and database credentials, use a managed secret store such as AWS Secrets Manager, or, where appropriate, Systems Manager Parameter Store. Then apply least privilege to the Lambda execution role. Give the function only the actions it needs on only the resources it needs. Avoid broad administrator policies. A thumbnail function should not have permission to delete every bucket in the account, just because it needs to read one source bucket and write one destination bucket. Directly invoking one Lambda from another is not automatically wrong. But for asynchronous, bursty, or failure-prone work, tight coupling can make the system harder to scale and recover. A queue such as SQS can decouple the producer from the worker. One part of the system puts work on the queue. Lambda workers pull and process that work as capacity becomes available. The queue absorbs bursts and gives you a place to manage retries and failures deliberately. Use SNS or Event Bridge when you need fan-out or event routing. Use direct invocation when the dependency and failure behavior are intentional. The goal is not to use every service. The goal is to choose a pattern that lets one slow component fail without taking the whole flow down with it. Here is a classic serverless failure mode. A Lambda function writes an object to an S3 bucket. That write triggers the same function again. The new invocation writes another object, which triggers another invocation, and the loop begins. That can create unexpected charges and consume available concurrency. Lambda now has built-in recursive loop detection for certain supported chains, including supported Lambda, S3, SQS, and SNS loops. By default, it can stop a detected chain after roughly 16 invocations. That protection is useful, but it is not the design. It does not cover every possible service chain, and it should not be your billing strategy. Prevent the loop in the first place. Before you deploy an S3-triggered function that writes files, separate the source from the destination. The simplest design is to use a different bucket for the output. Another safe pattern is to use separate prefixes in the same bucket. Then configure the trigger to match only the source prefix. For example, the function can react to uploads in incoming and write thumbnails to processed without triggering itself again. Also set alarms for unusual invocation counts or concurrency, and consider reserved concurrency to cap how far a function can scale while you investigate a problem. Those safeguards are valuable, but the core fix is still architectural. Do not let the function's own output match the event rule that invokes it. Quick recall check. Your Lambda function writes output to the same S3 location that triggers it. What pattern is this, and what risk does it create? It is a recursive invocation loop. The function can create a recursive chain that consumes concurrency and creates unexpected charges before protection or operational controls stop it. The fix is architectural. Write output to a separate bucket or to a prefix that does not match the event rule that invokes the function. Want to build an API without managing an application server? This pattern appears everywhere in AWS. A client sends an HTTP request to API Gateway. API Gateway invokes a Lambda function. The function reads from or writes to DynamoDB, then returns a response through the gateway. Each service handles a different job. API Gateway manages the HTTP interface, Lambda runs the application logic, and DynamoDB stores the data. AWS manages the underlying infrastructure, but you still need to design authentication, authorization, validation, error handling, and monitoring. Recognize the diagram. It is a common example of a managed, event-driven application architecture. Batch processing waits for a collection of data before working on it. Stream processing reacts as records arrive. A Kinesis data stream can carry a continuous flow of telemetry, click events, or application logs. Lambda can process those records in batches as they arrive, making it useful for near real-time enrichment, filtering, and routing. But the function does not scale independently of the stream. Throughput also depends on the stream's shard capacity, batch settings, processing time, and concurrency configuration. The exam-level lesson is still straightforward. Use a streaming service when you need to process a continuous, incremental flow of events rather than waiting for a nightly batch. Here are 4 more common Lambda patterns. For scheduled automation, Event Bridge or Event Bridge Scheduler can invoke Lambda on a timer. For IoT, device messages can trigger a function that filters, enriches, or routes data. For security automation, AWS config or another event source can invoke a function to evaluate or remediate a resource. And for AI workflows, Lambda can validate an upload or coordinate a call to a managed AI service. The pattern is always the same. An event happens, a focused function reacts, and the function performs or coordinates one clear task. For large models or heavy inference, evaluate the compute option carefully rather than assuming a standard Lambda function is the answer. One Lambda function is great for a focused task, but a workflow with multiple steps, branching decisions, retries, approvals, or long waits needs an orchestrator. AWS Step Functions coordinates those steps as a state machine. A workflow can call Lambda functions, other AWS services, or external work. It can track progress, retry failed steps, catch errors, run branches in parallel, and wait for a callback before continuing. That means you do not have to handwrite all of the glue code for a multi-step process. For long-running auditable workflows, standard step functions can run for up to a year. The key idea is simple. Lambda runs the task. Step functions coordinates the process. One brief bonus topic. AWS Lambda. MicroVMs are an advanced option for longer-lived, strongly isolated execution environments, such as interactive code sandboxes or isolated CI/CD workers. Do not let this complicate the core lesson. Standard Lambda functions are for short, focused, event-driven execution. MicroVMs are a specialized option for longer-lived isolated environments. For Cloud Practitioner and for the rest of this video, keep your attention on Lambda functions. You have a business process with several steps. Some must run in order, some can retry, one may wait for human approval, and the overall process could last far longer than a 15-minute Lambda invocation. Which AWS service coordinates that workflow? AWS Step Functions. It represents a workflow as a state machine and can coordinate Lambda functions, other AWS services, retries, branching decisions, parallel work, error handling, and long waits. Keep the core distinction simple. Lambda runs the task. Step functions coordinates the workflow. Lambda durable functions are an advanced alternative worth exploring later, but step functions is the key orchestration service to recognize here. If you remember 7 things, remember these. Lambda runs code on demand while AWS manages the underlying compute. Standard Lambda function billing is based primarily on request and compute duration, and memory affects resources and compute cost. Common triggers include S3, API Gateway, DynamoDB Streams, SQS, Kinesis, and Event Bridge. A Lambda invocation can run for up to 15 minutes. Some sources send individual events. Queues and streams can send batches. Do not depend on local memory or temporary files being available next time. Store important state outside the function. Use least privilege execution rules. Keep sensitive credentials in a managed secret store, not in source code. For multi-step workflows, think step functions. That is the exam level map. An event arrives, Lambda runs focused code, and you design the permissions, data flow, and failure handling. Final decision check. A company runs a steady 24/7 service with predictable demand. Should it use EC2 or Lambda? Do not choose automatically. If the workload is a persistent process, compare EC2 or containers first. If it is still made of short, event-driven tasks, Lambda may be a fit. Compare duration, latency, operational needs, and total cost? The answer comes from the workload, not from the word serverless. Let's land the whole video. You can now explain serverless in plain English. Your code runs when an event happens, while AWS manages the servers underneath. You know the workloads where standard Lambda functions fit best, and when to compare an instance-based or container option instead. You also know two beginner mistakes that matter. Do not store sensitive credentials in your source code. And do not let a function write output that matches the S3 event rule that invokes it. Recursive loop detection can help with certain supported chains, but safe architecture is the real protection. That is the video in 3 moves. Match the event to the function, match the workload to the compute model, and design the permissions and data flow deliberately. Up next in this series, Part 5. EC2 versus Lambda. Which should you use? We'll take the server-based versus serverless decision from this wrap-up and turn it into a simple decision rule, so you stop second-guessing your compute choices. If this series is making AWS finally click for you, hit subscribe, and I'll see you there. Careers are not built by watching videos. They are built by applying what you learn. This week, build one small event-driven project. Upload a file to an S3 source bucket, trigger a Lambda function, and write the result to a separate destination bucket or prefix. Give the function only the permissions it needs, then use CloudWatch logs to verify the flow. Document the architecture in one simple diagram and share what you learned. That is how you turn cloud knowledge into a portfolio project. Thanks for watching Hired in IT, where we are turning IT knowledge into career opportunities.